So today we're going to be talking about related rates. Related rates is really just using our knowledge of implicit differentiation to solve these application type problems involving calculus. So our question starts off like, Sarah blows up a spherical balloon. If the radius increases at a rate of 1 centimeter per second, how fast is the volume increasing when the radius is 10 centimeters? So our first step is always going to be to draw a diagram and label. So there isn't really much that we can draw in terms of a diagram for this question. But I mean, we can draw a sphere and we can label our radius in here. The next step is to write the equations for all given information in terms of calculus. So when I'm looking at this question, I see a couple of things. So the question is actually asking me, how fast is the volume increasing when the radius is 10 centimeters? When I look at the question further, I see some units are given. So what I'm really looking for is dV by dt. And I know this because it's telling me how fast the radius is increasing in terms of centimeters per second. So I know my volume is going to be increasing centimeters cubed per second. The only other piece of information that they gave me is the fact that the radius is increasing at a rate of 1 centimeter per second. So this is going to be my dr by dt, and we know that that is equal to 1 centimeter per second. So the next step is to write the formula that relates all of the information. Since this question is talking about a sphere, more particularly the volume of a sphere, we are going to be writing our formula, volume equals 4/3 pi r cubed. My fourth step is to take the derivative with respect to time. So I just rewrote the volume formula here since I'm on a new page. Now I know I'm taking the derivative with respect to time because we said earlier that our main goal, or what we're trying to find, is dV by dt. So if I go ahead and I take this derivative, I've got 4/3 pi. That's just a constant that I'm keeping here. I am multiplying by the derivative of r cubed, so 3r squared. But since I'm taking this derivative with respect to time, I still need to have my dr by dt here. Our last step is to sub in that information and solve. So dV by dt is what we're looking for and what we've always been looking for. I'm going to keep my 4/3 pi. 3. I can sub in my r. My r, remember, was given to me as 10. And my dr by dt was also given to me, and it was 1. So when I go through and I multiply all of this together, I'm going to be getting 1,256.64. And don't forget your units, especially with related rates. They're very important, centimeters cubed per second. For our second example, we're still going to be following the same 5 steps that we used for our first example. Sand is falling from a conveyor belt at a rate of 2.5 meters cubed per second into a conical pile. The pile of sand has a ratio of radius to height of 2:1, so the radius is always going to be double the height. How fast is the height changing when the radius is 6 meters? So the first thing that we did is draw this diagram, just a conical pile. I've labeled my H and my R. Sorry, my drawing skills are not that great, especially on an iPad with a stylus. The second thing that we're going to be doing is writing down all of the information that we know. So we know a couple of things. We know that it's falling from the conveyor belt at a rate of 2.5 meters cubed per second. So this is going to be my dV by dt. 2.5 meters cubed per second. The next thing that I know, or I want to know, is my dH by dt. So this says that I'm looking for how fast the height is changing. And the third and final thing that I guess I know, and definitely won't hurt to write down, is that we're looking for that how fast the height is changing when the radius is equal to 6 meters. Now from here, using a little bit of thinking, if I know that the ratio of radius to height is 2 to 1, so my radius is always going to be double my height, I can deduct that if my radius is 6, that means that at that point my height will be 3. So that just gives me one extra piece of information that I may or may not need. Now, if you can remember, my third step is to create a formula for this. So we have a conical pile. So the volume of this cone or conical pile is going to be 1/3 pi r squared h. Moving on, we have that fourth step, which is to take the derivative of this thing. So dv by dt is what we're going to be solving. Now when I look at this, I do see that I am going to have a product rule. I also have a constant out front. So I'm just going to go ahead and I'm going to leave this constant out front, and then I'm going to worry about using the product rule on that r squared and that h. So I'm going to do the derivative of the first, so 2r. Now since that isn't with respect to t, I need to add in that dr by dt and multiply by that original second function, so h, plus the derivative of the second function, which is just 1. Again, I didn't do that derivative with respect to t, so a dh by dt, and can't forget to multiply by that original first function. My fifth step is to go ahead and plug in all of that information. And when I look at this, I know my dv by dt, I don't know my dr by dt, and I don't know my dh by dt. So this is a problem. If I have two unknowns and only one equation, there's no way that I can solve this. So what we need to do is we need to go back and look at our equation again and our question again and see if there's something that we were maybe missing or another way that we could look at this problem. So with two unknowns, we can't solve. We already talked about this, but when I look at this equation that I have, I can think about something that I remember reading. So it said that the ratio of radius to height was 2 to 1. Now, based on this, I can write an equation that looks like r is equal to 2h. Now we know this, I said it a few times, the radius is always going to be double my height. But if I think about this and use this information in this equation, I'm able to rewrite this equation with only one variable. So I'm going to go ahead and I'm going to plug this in, and I'm going to say v is equal to 1/3 pi times 2h squared. So I replace that r with my 2h times h. So v is equal to 1/3 pi times 4h squared times h. V is equal to 1/3 pi times 4h cubed. At this point, I can go ahead and I can rederive this problem, and I'll be able to plug all of my information in and solve it properly. So before I start deriving this, I just simplified it a little bit further. 1/3 pi times 4 h cubed is equal to 4/3 pi h cubed. Now when I go ahead and derive this, I'm getting dv by dt is equal to 4/3 pi times 3h squared dh by dt, and now I'm able to go to step number 5 and plug in all of that information that I know or that I want to know. So I can go ahead and plug in that information that I know. dv by dt was 2.5. 4/3 pi times 3. We said that our height was 3, and our dh by dt is what we were solving for. So if I go ahead and I simplify this and I do 2.5 divided by that, I'm going to be able to get my dh by dt, and it's going to be 0.022. Don't forget about your units, meters per second. And I'm sorry if you heard or hear some crazy things going on. My husband and boys are playing Hungry Hungry Hippos, so it sounds a little crazy right now. A ladder 6.5 meters long leans against a vertical wall. If the foot of the ladder slips outward, so the foot of my ladder is going this way, at a rate of 1 meter per second, find the rate at which the top of the ladder is decreasing or descending the wall at the instant the foot is 2.5 meters from the wall. So I have my diagram here. Right away, I'm going to know that C is 6.5 meters long. C is my ladder. The other thing that they told me is that the foot of the ladder is slipping outward. So we already said it's moving this way. So it's actually increasing. So my dA by dt is actually a positive 1 meter per second. When I look at this last piece of information, it says find the rate at which the top of the ladder, so up here, is descending the wall. So I'm looking for this, how fast the top of that ladder is slipping down the wall. So I'm actually looking for dB by dt. And the last thing they tell me is that we're looking for this rate at the instant the foot of the ladder is 2.5 meters from the wall. So they are telling me that A is going to be equal to 2.5 meters. Now, when I look at this, right away I see a right triangle, and so I know that I'm going to have the formula A squared plus B squared is equal to C squared. I'm going to be able to take this A and this C, and I'm going to be able to solve just by plugging it in and rearranging. So 2.5 squared plus b squared is equal to 6.5 squared. And when I solve this, I'm going to get b is equal to 6 meters. Now, I'm going to rewrite this formula here. A squared plus b squared equals c squared. Now, when I look at this, the A and the B changes. So the distance, or the height, I guess, that my ladder reaches, or my B, and the distance it is away from the wall, my A, is always going to be moving, but my C, or my ladder, is going to remain constant. So my C is 6.5 meters no matter what. And yes, I know these lengths probably don't make sense. Probably should have been using feet instead of meters, but that's okay. So I'm going to have a squared plus b squared is equal to 6.5 squared. So when I'm thinking about my steps, I have a diagram, I've wrote my knowns and my unknown, I have my formula that I'm going to derive, and so I'm going to start and I'm going to derive this. So 2a dA by dt plus 2b dB by dt is equal to the derivative of a constant, so that is 0. Derivative of a constant is always 0. I can go ahead and plug in my information. So I know A, I know dA by dt, I know B, and dB by dt is what I'm solving for. So 2 times 2.5 times 1 plus 2 times b was 6 times dB by dt is equal to 0. So 5 plus 12 dB by dt is equal to 0. dB by dt is going to equal negative 5 over 12. Now this makes sense. We knew that the top of the ladder was slipping down, and so we knew that we should be getting a negative rate here. And we can't forget our units, and so this is going to be a velocity or a speed, and so we're going to be getting meters per second here.